Imagine walking into your very first computer science class, expecting to learn about how computers work, maybe how to build one, repair one, or at least understand what's going on inside that mysterious box sitting on your desk. You expect circuits, processors, RAM, maybe even how to assemble a machine from scratch. But instead, the instructor starts talking about logic, problem solving, algorithms, and abstract thinking. There's barely any mention of actual computers. That moment feels confusing, almost misleading. If this is computer science, then where are the computers? This confusion comes from a deeply rooted misconception that computer science is about computers. It sounds obvious, even logical, but in reality, it's fundamentally wrong. Computer science is not about computers in the same way that astronomy is not about telescopes or biology is not about microscopes. Computers are tools, powerful ones, but they are not the essence of the field. The true core of computer science lies in understanding how to solve problems, how to represent information, and how to design systems that can process that information efficiently and correctly. At its heart, computer science is about computation. And computation is simply the process of taking some input, applying a set of rules or steps, and producing an output. That's it. This idea existed long before modern computers were ever invented. Humans have been performing computations for thousands of years using pen and paper, mechanical devices, or even just mental calculations. The word computer itself originally referred to a person who performed calculations. Machines came later. So when we talk about computer science, we're really talking about the science of solving problems using well-defined procedures. These procedures are called algorithms. An algorithm is just a step-by-step method for solving a problem, like a recipe for cooking. It doesn't matter whether a human follows the steps or a machine does. The logic remains the same. Think about something as simple as sorting a list of numbers. You could do it manually by comparing numbers one by one, or you could write a program to do it for you. But the interesting part, the science part, is figuring out the most efficient way to do it. Should you compare each pair? Should you divide the list into smaller parts? How many steps will it take as the list gets bigger? These questions have nothing to do with the physical computer. They are about logic, efficiency, and mathematical reasoning. This is why computer science is often described as a branch of mathematics rather than engineering. While engineering focuses on building physical systems, computer science focuses on abstract concepts. It deals with questions like, what problems can be solved using algorithms? How quickly can they be solved? Are there problems that cannot be solved at all? These are deep, theoretical questions that go far beyond the hardware. Abstraction means hiding unnecessary details so you can focus on the bigger picture. When you use a smartphone, you don't need to understand how electrons move through circuits to send a message. You interact with apps, icons, and interfaces that simplify complex processes. Computer scientists design these layers of abstraction so that systems become manageable and usable. Programming languages are a perfect example of abstraction. Instead of writing instructions in raw machine code, long strings of zeros and ones, you use languages like Python, Java, or C++. These languages allow you to express ideas more naturally and clearly. But again, the language itself is not the core of computer science. It's just a tool for expressing algorithms and logic. Another key concept is data. Everything in computing revolves around data numbers, text, images, videos, and more. Computer science explores how to represent data efficiently, how to store it, how to retrieve it quickly, and how to transform it into useful information. Data structures, such as arrays, lists, trees, and graphs, are ways of organizing data so that algorithms can work effectively. Choosing the right data structure can make a huge difference in performance. Now, consider the idea of efficiency. Not all solutions to a problem are equal. Some algorithms might solve a problem quickly, while others might take an impractical amount of time. Computer science provides tools to analyze and compare these solutions. This is where concepts like time complexity and space complexity come into play. They help us understand how an algorithm scales as the size of the input grows. For example, imagine searching for a name in a phone book. You could start from the first page and check each name one by one. That works, but it's slow. A better approach is to open the book in the middle, see if the name comes before or after, and then narrow down your search. This method is much faster, and it illustrates how a smarter algorithm can dramatically improve performance. Computer science also deals with the limits of computation. Some problems are incredibly difficult, even for the most powerful computers. Others are impossible to solve with any algorithm. Understanding these limits is a crucial part of the field. It helps us focus on what's achievable and guides us in finding approximate or alternative solutions when exact ones are not feasible. Another fascinating aspect is the idea of automation. Computer science is about designing systems that can perform tasks automatically without human intervention. This could be anything from sorting data to controlling robots to powering artificial intelligence. But again, the emphasis is not on the machine itself, it's on the logic that drives the machine. Artificial intelligence is a great example of this. When people think of AI, they often imagine robots or futuristic machines. But at its core, AI is about algorithms that can learn from data, recognize patterns, and make decisions. It's about creating systems that can mimic certain aspects of human intelligence. The hardware is just the platform. The real innovation lies in the algorithms and models. The same applies to fields like cybersecurity, databases, and networking. In cybersecurity, the focus is on protecting information and ensuring secure communication. In databases, it's about organizing and managing large amounts of data efficiently. In networking, it's about designing systems that allow computers to communicate with each other. In all these areas, the underlying principles are rooted in logic, mathematics, and problem solving. So why do people associate computer science so strongly with computers? Partly because computers are the most visible application of the field. They are the tools that bring abstract ideas to life. Without computers, many of these concepts would remain theoretical. But just because computers are essential tools doesn't mean they define the discipline. Think of it like writing. The study of literature is not about pens or keyboards. It's about storytelling, language, and expression. Similarly, computer science is about computation, not computers. The tools may change over time. Today's computers are vastly different from those of a few decades ago, but the fundamental principles remain the same. This distinction becomes even more important when you consider the future. Technology is evolving rapidly, and new types of computing devices are emerging, such as quantum computers. These machines operate on entirely different principles than traditional computers. Yet, the core ideas of computer science, algorithms, data, abstraction still apply. This shows that the field is not tied to any specific technology. Understanding that computer science is not about computers can change the way you approach learning. Instead of focusing on memorizing programming languages or tools, you start focusing on thinking skills. You learn how to break down complex problems into smaller parts, how to design solutions, and how to evaluate their effectiveness. These skills are valuable far beyond the world of computing. In fact, computational thinking is becoming an essential skill in many fields. Scientists use it to analyze data, economists use it to model systems, and artists use it to create digital works. The ability to think algorithmically, to approach problems in a structured and logical way is increasingly important in a world driven by information. There's also a philosophical dimension to computer science. It raises questions about the nature of intelligence, the limits of knowledge, and the relationship between humans and machines. Can a machine truly think? What does it mean for a problem to be unsolvable? These are not just technical questions. They touch on deep aspects of human understanding. At the same time, computer science is highly practical. It has led to innovations that have transformed every aspect of modern life, from communication and transportation to healthcare and entertainment. But these applications are built on a foundation of abstract ideas. Without that foundation, the technology would not exist. It's also worth noting that computer science is a constantly evolving field. New problems emerge, new techniques are developed, and new areas of research are explored. What remains constant is the focus on problem solving and computation. This makes it a dynamic and exciting discipline, full of opportunities for discovery and innovation. So the next time someone says that computer science is about computers, you can challenge that idea. Computers are just the tools, the instruments that execute the ideas. The real essence of computer science lies in the ideas themselves, in the logic, the algorithms, the structures, and the ways of thinking that allow us to solve problems and understand complex systems. In the end, computer science is not about machines. It's about the human ability to think, to reason, and to create solutions. It's about turning ideas into processes and processes into results. It's about understanding how to transform information in meaningful ways. And while computers play a crucial role in this journey, they are only the beginning, not the destination.